So speaking of the beauty of 19th century mathematics, 19世纪的数学 beautiful stuff. So just I thank some of you for a comment on the way we look at this identity, right? Let's come back to look at Parseval's theorem. I say it preserves the norm, and this is a special property. Okay, why? Because Fourier transform can be regarded, I want you to remember, Fourier transform can be regarded as a change of basis. 辉转换是坐标变换啊 A change of basis from time domain, and now we choose a different basis set, different basis. 基底的这个变换 The basis is going to be the set of all e to the j omega n. Yeah, change of basis. Now, so that the index changes from n to omega, right? Think of it as a change of some change of basis, okay, for any vector space. Yeah, and we know that when we all know that for any vector space, the basis is not unique, right? Generally, basis can be changed, right? It's not unique, 并不是唯一的. There are multiple ways of representing a vector using a different set of bases, right? But here, in general, when you change basis, then you calculate the norm, the result is going to change, right? Because you can stretch in one dimension and compress it into the other dimension, and the length of the vector is not going to be 1 over 2 pi times the original length. Whenever you change the basis, most likely, generally speaking, the norm is not preserved. But here, Fourier transform is a special kind of change of basis which preserves the norm. So this is special. This is worth noticing, okay? Worth mentioning. It's special. In general, any change of basis will not preserve the norm. So that's one reason I say it's beautiful in the from the angle of changing basis. Right? When we think of Fourier transform as a change of basis, you're representing your signal in the frequency domain. That's a change of basis. Fourier transform preserves the norm, and so this is indeed one thing I want to mention to you, but. Otherwise, in the textbook, this is some additional remarks I want to also mention to you. If you're interested, there's some materials you can extend your reading, okay, about DTFT. So DTFT here, if you talk about the existence of DTFT, we are not talking about, okay, existence means that the summation converges or not. Okay? If the summation converges, then we call, the Fourier transform exists. So here's the first notion. The first notion gives us a sufficient but not necessary condition for DTFT to converge. So let me read it first. So this is a known property that if x in the time domain is absolutely summable, absolutely, when we sum up all the absolute values of all samples, when the signal is absolutely summable, less than infinity, absolutely summable, then this sequence, that's the definition of DTFT, by the way, right? Let's notice, please be aware that this is the definition of DTFT. If the x is absolutely summable, then DTFT converges for any omega. Nice. Sufficient, okay? Sufficient to guarantee that DTFT converges, so there's no worry. It can be calculated, it exists. So that's a notion of existence. 所谓的存在, in this context, what we call existence just merely means that we are asking whether or not this summation converges. Okay? And there is a sufficient condition right here. If this happens, no worry. Okay? DTFT can be calculated, it exists. And that's the first notion. The second notion is, if you look at it briefly, you might find it absurd. 看起来很蠢啊. This might look absurd. Absurd. It's a nice word.公众英语教室. Absurd. it might be a little bit absurd, stupid to look at first, right? But so let me explain. The second notion is that, well, what if x is not absolutely summable, right? We have said that if x is absolutely summable, then no worry, DTFT exists, right? But what if it is not absolutely summable? Can we still talk about DTFT? That's a valid question. That's a valid concern, okay? That's a valid concern. Well, so there's now 19th century mathematics tells us that if x is not absolutely summable, if it diverges, if this diverges, but the sum of square converges, all right? Yeah. Then we just need a more careful definition of DTFT. Okay? Then let us define DTFT as the limit, a limit. Limit of what? The limit of taking this finite summation first, then let big N let it go to infinity. Looks stupid, right? Right. That's a second notion. It's a worry of a kind of rare case. What if the signal is not absolutely summable, but the square of a signal is absolutely summable? Then we can refine our definition. Just be a bit more careful. Now, be a bit more careful. We define DTFE as the limit of a finite sum. And then we first evaluate the finite sum here, negative n to plus n. That's an important detail right here. Okay. If you define DTFT as such, then still there's no worry. Then this converges. Okay. Then this very definition, this newer, slightly more refined definition, converges for all omega. Okay. So this is kind of the first transform is deep. This is so just in case you're interested, just talk to me. Right. So why do I think this might look a little bit absurd to be at the beginning? Right. But the textbook has you can find this kind of discussion also in the textbook, right? But this is optional, right? So with that, I would like to just conclude our kind of a brief introduction of selective properties for DTFT. What do we have? Periodicity, 5 properties, right? Periodicity, symmetry, 2 kinds of symmetry, and the next is convolution theorem, shift theorem, and the Parseval theorem. So those are the selective properties I'd like to sort of summarize in one lecture, right? But with that, any comment? Yeah. Talk to me if you are interested, because I am. I'm interested in that. Right. So let me now switch to my next lecture. Okay, my next lecture. So yeah. So now I'd like to switch to a new topic. Okay, this is the last lecture of this on chapter 4. Okay, in chapter 4 we are all about sampling and the relation between discrete time and continuous time. Okay, but there's one last issue, important issue that we need to talk about. Really making the signal digital. The signal can be make digital so that we can process it with computers, right? We need to represent numbers by digits. Yeah. So digital signal, just if you want to be sure, a digital signal has to be, you need to talk about how we represent numbers. So this is the time we talk about number representation, okay? How do we encode a number, any real number, by, let's say, 8 bits? How do we do that? So let's take a kind of a review, a summary on that. So this lecture is about finally making the signal digital, and then we can talk about digital processing of analog signals, and there the main issue is called quantization. When we encode any real number, that encoding introduces error. Just inevitably, 无可避免, when we just represent a real number by finite resolution, by just 8 bits, 16 bits, 32 bits, 64 bits, just inevitably there will be an error of rounding. 做四舍五入的时候 we'll see that basically to encode a real number, we recommend using rounding. Okay, 用四舍五入 But then after 四舍五入 after rounding, the fractional part, 小数的部分 is abandoned, right? So that introduces a kind of error, which we call quantization noise. Error is noise. Error is noisy. Error is unwanted. Okay. Yeah. So with that, let's come to the first slide. So this first slide is a sort of a review. Here on the left we have a continuous time signal, and we can just convert it to discrete time, and the result becomes a sequence of number with, and then here you can also specify a sampling rate, sampling period. And everything can happen in the discrete time domain. And then in the end, you might want to we want to just output your signal. Okay, so that is to say you might want to convert your signal from discrete back to the continuous time using the same sampling period. Okay, so this chain of processing is called discrete time processing or filtering of continuous time signals. Yeah. But now that's a kind of ideal scenario. It's too simplified. 太过于简化, too simplified. So it does not talk about how we actually represent the number, right? The numbers. So here is a more complete chain of blocks that we need to be aware of. So first of all, still with the continuous time signal, because we want to prevent aliasing, you need to low pass the signal first. Okay. Low pass to ensure that the bandwidth is what? Narrower than 1/2 of your sampling rate, right? So this first preliminary step is called anti-aliasing. Anti-aliasing, you want to apply a low pass filter. Make sure the bandwidth now here is less than or equal to 1/2 of a sampling rate, okay? All right, so after anti-aliasing filter, then to convert to discrete time, there is sample and hold, which we'll explain in the next slide. That's the next step. And after that, we are now ready to convert real numbers to a digital representation. So digital representation, and in the end, we do the opposite. D2A converter, and there is a compensated reconstruction filter, which we briefly talked about when we introduced D2A conversion a few weeks ago. So let me summarize with you a few practical issues. Okay. The first practical issue is that continuous time signals are not precisely band limited. Continuous time signals, strictly speaking, has extended bandwidth, right? So you need to practically just do the low pass filter, okay? Whenever if you are going to sample your signal next, so it's absolutely recommended that we want to prevent aliasing. Limit your bandwidth first to ensure that there will be no aliasing. That's one practical issue, number one. And there's another practical issue that ideal low-pass filter actually cannot be realized. What's that about? Ideal low-pass filter, maybe it's we can talk about it. Ideal low-pass filter, does anybody remember? Ideal low-pass filter has a inverse Fourier transform, right? So ideal low-pass filter in the frequency domain with a cutoff frequency omega c minus omega c in continuous frequency domain. When you think about this, back in the time domain, what's the result? Sinc, right? This is a kind of a sinc function. But sinc function, if you really think about it, this is problematic. I said this cannot be implemented. Ideal is ideal. Ideal means it's not real. It's not practical, right? I said that sinc interpolation cannot be implemented. Why? There are a few reasons. First reason is that in the time domain, it extends from minus infinity to infinity. So, I mean, this property alone makes it impractical. Yeah. This just simply cannot be implemented, right? So keep in mind that this is not the focus of our study right here. I'm pretty sure that A to D conversion has a lot of details that itself is a field, itself is a specialty. If you're really interested in ADC, maybe you may want to speak to Professor Xie Zhicheng. I think he specializes in that. So, but keep in mind this, this thing really cannot be implemented. It lasts forever. Cannot be. It needs to be approximated. The best we can do, the best anti-aliasing filter we can do is never ideal. It's an approximation of ideal filter. Okay, all we can do is approximation. So that's the second practical issue. And the third practical issue is that ideal C to D and D to C conversion does not worry about quantization, but now we need to start to worry about it. Okay, we need to start worry about how many bits do we have and how much quantization error that will introduce. Right. So this again, ideal C to D or D to C are both ideal concepts. Right. In practice, they need to be replaced. They can be approximated by A to D and D to A conversion. A stands for analog, D stands for digital. Right. So with those are a few remarks in mind. So here is the outline for this lecture. So in the next slide, next few slides, I will just briefly first talk about sample and hold. Very simple idea. And then following that, we go to the issue of quantization and the noise it introduces. We'll talk about binary representation of numbers. We'll talk about some properties of the noise that's introduced by quantization, by rounding. Okay, when we represent numbers by binary representations, then we will encounter noise, and we will study the noise property, its distribution, and its spectrum. Two different ideas. Okay, so with that, let's talk about sample and hold first. So to sample and hold means you to something right here. Okay. So here, suppose that we have a continuous time signal, and we have a sampling period t. To sample and hold, just literally, literal means that we measure the signal and then hold it. That's all. We take a measurement of a signal right here, for example, at this moment, minus 3t, and then hold it. And after t, after a period of t, then we repeat the process. We sample the signal. And we make a measurement right there. The signal is so much. Then we hold. The system holds right there. So that's why it's called sample and hold. Sample and hold. Sample and hold. Sample and hold. Okay, very simple idea shown in this picture. But why do we hold? We hold that's because then that gives us some freedom to make the conversion. Okay, as long as we can finish the A to D conversion within this much of time, we are fine. Okay, sometimes it takes longer. Sometimes it takes we're almost running out of time. Sometimes we can just do the conversion right away. Doesn't matter. As long as you can finish the conversion within a period of t, that's okay. Sample and hold. Hold it first, then ask this next block to do the conversion. Okay? So that being said, that means everything here is ignored. Okay? Anything in between sample time is going to be ignored. So that's the idea of sample and hold, so as we can make the conversion. Okay, so what do we mean conversion? Any questions here? Anything? Does everything look okay right here? Very simple idea, sample and hold. Okay. And then so now that's sample and hold. Okay, and that's the overall block diagram. But here, let me say that to perform sample and hold and then convert it to digital domain. These two blocks are equivalent to 2 steps. They are equivalent. They're equivalent to converting to discrete time first, then perform quantization. Okay? Converting to discrete time first, then perform quantization. And quantization, the result of quantization is going to be denoted as using a hat right here. 一个帽子 hat, hat. So let's denote the result after quantization as x hat. And b, here without b, it doesn't really matter. But hat means after quantization. Right? So I also need to define a few things, a few terms. First of all is this symbol right here, denoted as xm. It stands for the kind of maximum scale, the full scale, the full scale. Yeah. So let's say xm is called, you can call it full scale in the sense that we are going to limit our signal between minus of the full scale to plus full scale. The signal is going to be limited. Okay, the signal value is going to be limited from minus to plus that full scale. Everything beyond that range, what can we do? There's nothing we can do. We'll simply clip the signal. 我们就让它截断了. Yeah, okay. We'll simply clip the signal. There will be examples. Okay. So full scale means that your signal may look like this to begin with, but before we talk about quantization, we need to first define what's the desired range. Okay, what's the kind of minimum to maximum range? So let's say our range is going to be plus to minus the full scale. So let's define our full scale to be within this range. So that means that later on we'll see anything that's beyond this, anything that's beyond this is just going to be clipped. Okay, it's just going to be clipped. So now the signal will not be encoded. So anything that's larger than plus m or more negative than minus xm will be simply. We will simply say sorry. We are reaching out of the range. Okay, so that's the meaning of full scale. Okay, so it's an important parameter regarding the design right here. First define the full scale here. Then we can talk about representation. Okay, then finally, in all the samples right here, then we can talk about how do we convert all the samples into a sequence of, let's say, 8 bits, a sequence of 16 bits for every real number right here. Okay? So far, so good? So we have one parameter called xm, and the other parameter is denoted as b. That's the number of bits. Okay, essentially the number of bits. And let's look at an example first. Okay, so in the next slide, I'm going to show you an example. So this is an important figure. Okay, let's figure out. We say that this in the textbook says that this is a typical quantizer for discussion for education purposes. Quantizer for AD conversion. Okay, what does that mean? So this is a I/O plot. Input for x, output in the vertical axis. Okay, this is an I/O plot. And what do we see here? What do you see here? Like steps, right? Staircase. It looks like a staircase. 看这样楼梯嘛, yeah. So this is an I/O plot. So here on the right, so how do I explain? So first, if you count how many steps right here, what do we have? We have 1 level, 2 level, 3 level, 4, 5 in the middle, 6, 7, 8. 8 levels. Okay, 8 levels can be represented by 3 bits. Yeah. 8 levels can be represented by 3 bits. Okay, so you can now define how are you going to use 3 bits to represent each level. Now we are ready to talk about how we represent each level, but there in this example, there are 8 levels. Agree? So A level, and we separate the level by a step size called delta, quantization step size. So in the negative end, the output will be minus delta, minus 2 delta, or minus 3 delta, and so on. On the positive side, the output can be 0 for sure, or delta, 2 delta, or 3 delta. So 8 levels. And we have a quantization step size that's, and we are going to represent the output as integer multiple of delta. Okay, 8 different levels. It should be pretty clear, from minus 4 delta to 3 delta. 8 different levels. So far, so good? Huh? All right. So now, 8 different levels. So conceptually, I'm going to say this first. Conceptually, I'm going to say that, okay, since the full range is 2xm, right? 2xm should be equal to, in this example, A times delta. Can we agree on that? Roughly speaking. Roughly speaking. So delta is equal to 2xm divided by A. Now what is A? 8 is 2 to the 3rd power. Okay? So this is a relation between how many bits we have, what's the full scale, and what's the quantization step size. Roughly speaking. Okay, so that's what I'm going to say right here. We have delta equals to that. Okay, 2 times the full scale divided by 2 to the power of how many bits we have. Okay. It's kind of sad that here we really cannot represent 4 delta, right? And on the negative side, there's a little remark right here. On the negative side, we were able to represent minus 4 delta. But now we lose the capability to represent 4 delta because that will be an extra level. So there's a bit of asymmetry right here, 不太对称. You represent this side, you lose the ability to represent that side. Okay, that point is something that we need to compromise. But roughly speaking, I want to just share with you 2 times the full scale equals to 8 times quantization step. And 8 here is 2 to the 3rd power. 3 being what? 3 being the number of bits. Okay, number of bits. So now one code for each level. So now there are different options. So here the first option has a name 2's complement. I'm not sure, have you all learned about what's 2's complement? 在哪门课? In which course? Logic design. Oh, great. When I was a college student, there was a class called 计算机概论, Introduction to Computers. You don't have that, right? Good for you. It's a boring class. That's where I learned 2's complement. So this is 2's complement. It's easier to understand. So let's take a quick review here. To the positive side, 0 means 0, right? And this is binary 1, right? So 1 represents 1 delta, 2 represents 2 delta, 3 represents 3 delta. Okay, that's very straightforward. 非常直截了当. But what happened right here? It's like 0, 1, 2, 3, 4, 5, 6, 7. That's the scheme, the 2's complement way of encoding your number. Okay? Encoding the number 0 to 3 and minus 4 back to minus 1. Okay? So that's an example, and you can just also generalize what if we have 3 bits, 4 bits, 5 bits, or more bits to represent, to encode your numbers. Still, 2's complement goes from 0 to 1, 1, 1, 1, 1, and back to most negative level, and then it increases it goes back to 0. Yeah, that's 2's complement. Okay, take a look, 2's complement. Yeah, and just to take a last look of this figure, we haven't talked about here, right here. What's going on right here? So this relation is going to give you the nearest integer multiple. You know, it's about finding the nearest integer. Okay, for example, here between 0.5 delta and 1.5 delta, between here, the nearest integer is delta. Right? I mean, the nearest integer multiple of delta is 1 delta. Right? 0.5, 1.5, the nearest integer is 1. Of course, you need to specify what if the value is exactly this. Does it go here? Does it go to the next level? Do we just round up or round down? Yeah? So, but anyway, so the idea, the kind of basic idea is to find the nearest integer. So that's what quantization is about. Quantization is about finding the nearest integer or rounding. Simply in Chinese, 42 rule. Very, very simple. Yeah? So that's why we get a staircase shape right here for quantization. And in next, let's do an exercise. Okay, exercise time. Yeah. Well, so this is the plot to remind ourselves this is what we have when we have 3 bits. But what if we have now 8 bits? 8 bits. And I need you to tell us, help me, what does this encode? What does this code correspond to? What does it represent? How many delta does it represent? Okay, yeah. So I give you some, maybe 2 minutes, and we can check the answer. Right? How many delta and does it represent? How many delta? Now we have 8 bits. Suppose that we use 2's complement, by the way. Okay, let's use 2's complement. Okay, so question is, what is this number in 2's complement? Okay, anybody? Does anybody have an answer right now? How many delta? 1. What do we have? 1, 2, 0, 0, 0, 1, 0, 0, 1. Okay. How many delta? First of all, the first bit is 1, right? So this is negative. Okay. First, we want to notice that this is negative. Okay. This is negative. How about here? How about here? In the textbook, it has a formula, actually. This is about if this is B0, B1, each bit. So if this is a sequence, a string, 一个字串, if this is a binary string, denoted as B0 to B7. In the textbook, actually, you find a formula. There is a formula. There is a formula. I hope I can be correct. The formula that this equals to what? Minus 2 minus B0 times 2 to the 0th power, okay? Plus B1 2 to the minus 1 power plus B2, I write one more term. So that's a formula given by, you can find it on the textbook, okay? But you probably have learned that 2's complement is much more simple than that, right? It's much more simple. So what do we do? Can somebody tell me? What do we do next after figuring out it's negative? 2's complement, right? 2's complement. What does complement mean? 反过来, complement means opposite. So now the suggestion, a lot of you might have learned this. Let's review. So 反过来, so let's flip the 1 to 0. Whenever you see a 1, write 0. Whenever you see a 0, write 1. Yeah? Okay, 2's complement. Because that's the way the complete, no, not complete, complement. Okay. Complements means to do the opposite. Okay, to flip 1, you keep the 1 here, but for the next 7 bits, change 1 to 0 and change 0 to 1. Okay, 1 to 0, 0 to 1, 1 to 0, 0 to 1, and then what? And what do we do? And then do the binary representation of these 3 bits, right? So what does it represent? Can anybody tell me? 2加4, 2 plus 2 plus 4 plus 16 plus 32, right? What's the result? So this is 32 in decimal, 16 in decimal, 4 in decimal, and 2 plus, you just sum them up. What do we have? 54. So the answer is minus 54 delta. Huh? Oh, I forgot to plus 1, right? I forgot to plus 1, yes, thank you. The answer is so I'm, 还要再加1啊，所以 you need to add 1 啊。And this should be the same as equivalent to that, okay? 再加1, so then, so the answer is with the minus sign in the beginning. So the answer is minus 55 delta. Okay, so that's what this string, this binary string, represents in quantization. Right? So that's a nice little exercise, and which corresponds to this formula on the textbook. Yeah, this should be. Yeah, exactly. Yeah. So it depends. So this, I argue this is probably, if you multiply by full range, that might be what it is trying to say. Okay. Because full range, why? Because full range now is going to be 2 to the what? 7th power delta, full scale. Yeah, plus or minus full scale, right? And we have 8 bits, which means we have so many levels to represent. So I think everything put together, this is equivalent to that. Thanks for pointing out. This is a factor of 2 to the 7th right here. All right, so very good comment. And shall we now move on to the kind of core concept I want you to take home. I want you to take home today that, yeah, sure, quantization is about finding the nearest integer. And secondly, please now try to think about this as something that will introduce noise. There will be quantization error, right? Because quantization is an approximation. We are approximate our real numbers with only 128 different levels. I mean, 256, for example. So this is an approximation. By abandoning the fractional part, then we introduce approximation error. And error is, we want to think of error as what is shown in this diagram. Okay, so let's take a look. This diagram shows that when we perform quantization, you can think equivalently as if we have a signal for sure, and then we are introducing error. So that's kind of the key message I want you to take home today and think about it. Okay, quantization is equivalent to introducing some sort of error because it is an approximation process. Because we are finding the nearest integer, thereby abandoning the fractional part. 小数点以下不看了, right? Well, it's rounding. So finding the nearest integer introduce this error, and we call this error. We can think of error as something being introduced. The two of them add to, and the result is the result has a hat. Okay, So this result is after quantization. X hat as a function of x. Okay, x hat, sure, is a function of x, but you can equivalently think of it as if x hat is x plus error. Okay, x plus error. So something for you to ponder upon, right? And this is important. Okay? Any comment here? Is it clear what I'm trying to say? Is it clear to all of you? Anybody? Introducing error. Okay, quantization introduces error. Okay, so quantization introduces error. And here is a nice little example on the textbook. Okay, suppose that we have a signal and it's discrete time. The signal is 0.99 times cosine with a period of something, right? Suppose that this is a signal like that. And then in this example, how many levels do we have? We have, again, 8 possible levels. 8 possible levels using 3-bit, right? And now suppose that, suppose that our scale, full scale is 1, okay? So we can represent anything from -1 to almost 1, but the last level cannot be encoded. So we need to abandon the last level, the highest level. So maximum now is clipped at 0.75, 0.75. That's the meaning. Okay? When you decide the maximum range, then the signal is going to be clipped. Whenever the signal goes out of the range, okay, it's clipped on top, and it's also clipped, sort of clipped at the bottom. So in this some period of time, you find that the nearest integer nearest level is -1. The nearest level is -1. So that's a kind of a nice little example of what's happening before quantization and after quantization. And of course, it introduces error. Okay? It introduces error. So what is error? Error is defined by the output subtracted by the input. 输出减输入叫做 error. Yeah. So let's take a note. So here, error, quantization error. Error is defined as the output subtracted by the input. That's the definition, the usual definition of error. So therefore, we can think of the input as if that is suffering from some extra thing, extra noise right here, and the result is our output of quantization. Okay, output of quantization is denoted as Q of xn. So that's the overall picture. Before and after quantization. Okay. So the next slide, we look at the error. Okay. So now, if you just mentally calculate the difference, that's the error. This thing output subtracted by the input. That's the definition of error. Okay. So the next slide, now we take a look at the error. Error looks like that. The error looks like that. If we subtract the input from the output, okay? 输出减输入, if we subtract the input from the output, this is how the error looks like for this example. Could be positive, could be negative. Okay? Very simple. And this is what? What's that? The next plot is when we have 8-bit instead of only 3 bits, this is the error we have. Okay? Now, this error, the first thing we should notice that is the level, of course, becomes smaller. Yeah, of course, the noise level becomes smaller. Very simple stuff. Yeah. Using more bits, you have a finer representation, the error is smaller. Yeah, makes sense, right? So that's from the textbook. So next week, when we come back, we will finish this lecture. But let me just give you a quick preview, okay? So the quick preview is that now from here, if you just look at this last plot right there, does it look random? That's the question. This thing, and compared to 3 bits versus 8 bits, right? I think we can sort of see that this looks more random than that. This thing is not really random. I mean, it's random right here, but no, the shape shows up, right? So it's not really random here, not random here, but maybe in here it looks random. But this looks more random than that. Yeah, okay? Just by inspection, 用看的嘛, by inspection, by just simply visualizing the error, this thing indeed looks more random. But when we say more random, what do we really mean, right? Like tomorrow's discussion session is going to be selected randomly, right? What do you mean random? How random is random? So in probability, this is a few occasions that in this semester that we will need to borrow from probability, okay? So we need some kind of more rigorous definition when we talk about randomness, okay? Do we mean that it's more uniformly distributed? Or do we mean that it's a random process in which every sample is independent to other samples? Right? So those are already two different notions of randomness. 两种关于 random 不同的想法啊。So next week when we come back, we talk about a more rigorous definition of randomness. Are we talking about uniform distribution? Or are we talking about, if it's uniform distribution, we can calculate its expected value and so on, right? Probability, seriously. But there's also other properties that we need to mention. We can talk about whether there's some sequence of error. As a random process, how about its spectrum? Yeah. Is every sample independent of the next sample? If it happens, then we call that is what? Is identical, what? IID. IID. There is what? IID. Independent, identically distributed. All right. Yeah, so there are different notions of randomness that's worth mentioning. But we will talk about that next week when we come back. All right. So tomorrow, please come back here, and we'll have the first follow-up discussion. Okay. Yeah. Thank you for being here, and yeah, class dismissed.